All right, everyone. Well, welcome to class today. We're going to be talking about what I call, um, well, I don't call it that, but it's basically a chapter 9 substitute. Chapter 9 is a very interesting chapter in the book. It has a lot of brain anatomy, but I decided to tailor this lecture based more on the physiology as well as some things that people find interesting, like, for example, uh, different neurotransmitters and different types of medicines that attempt to increase levels of those neurotransmitters in the synapse. Also, we're going to talk about some disorders that affect the neuromuscular junction, and that will be interesting. We'll kind of continue on what we talked about chapter 8. And lastly, we're going to talk about head injuries. So some pretty interesting stuff. But the first thing that we are going to talk about with the central nervous system are the three fluid compartments. CNS stands for central nervous system. And we have a couple of environments here. And the first is that we have the blood in the form of capillaries, mainly. If you ever been to Body Worlds, the exhibit, they have something where it shows you, I think it's in like a glass case or something, but it shows you all the blood vessels contained in the brain. It just is a huge mass, of capillaries. And that's because the brain needs a lot of nutrients and a lot of oxygen. And as we know, that's only carried in the blood. Well, if you didn't know that, you do now. All right, so we have the blood, and the blood is actually going to be made up of, if you take an anatomy, simple squamous cells. I'm going to go ahead and just layer one side with simple squamous cells. These cells, as you remember, they are the thinnest type of cell, kind of look like a pancake. And because of their small size, they're ideal for diffusing gases as well as other things. But one thing that we haven't talked about, and I don't know if we'll be able to talk about it too much, is that the space between these cells here, the space between these simple squamous cells, even though they're connected by tight junctions, they're still leaky, meaning that things can squeeze through, including things even like bacteria. We don't want that in the brain. No, the brain is a very tight, controlled environment. So you may recall me talking about the astrocytes, chapter 8. And if you look here, these astrocytes, what they do is that they project these star-like structures. What they do is that they reinforce the capillary walls here to prevent things from leaking out. So what this does is it creates an extremely selectively permeable environment. And we know that the blood contains lots of nutrients. I think I covered that on the very first lecture. Well, also, so the first environment is going to be the blood, as I was saying. Now, the next part is going to be the interstitial fluid. So we know that the brain has a lot of neurons. And these neurons even have a tremendous amount of synapses. In fact, one neuron in the brain can synapse with up to 1,000 other different neurons, which is insane. So if you think about it, well, not if you think about it, but I was reading research a little while ago that said that the neuron, they think that each neuron functions like a computer. Each neuron is an integrating center. And you just have a bunch of these tiny computers just sending signals back and forth, which of course makes up our cognitive and autonomic systems. So super interesting. Also, something else I read that was interesting is when we're kids, we tend to think that things last a lot longer than they do. For example, I remember as a kid that 5 minutes felt like forever. And now five minutes feels like a second. And they think it's because that over time, the neurons that process visual stimuli actually degrade as you get older. And there's actually gaps in sense perception. So it's almost like we're we're missing frames. So we're not capturing all the information as we did when we were younger. Very interesting hypothesis. All right, so the space between the neurons is called the interstitial fluid. Okay, now the third environment, and this is going to be surrounding the brain and spinal cord, and it's actually going to be secreted by what we call ependymal cells. So I'm going to draw here. So this again is blood vessels that are innervating the brain. It's going to be surrounded by a type of cell called an ependymal cell. Kind of looks like this. And what these ependymal cells do is they secrete cerebrospinal fluid into the brain ventricles, which is an incredibly important fluid for numerous reasons. So we're going to go ahead and talk about those reasons now. So the cerebrospinal fluid actually surrounds the brain, and it's very important that we have it. If we didn't, every time you shake your head, your brain would smash around like a brain in an empty container. We don't really want that. That sounds like a terrible idea. Just having irreversible brain trauma every time you nod your head yes, that would be terrifying. We're going to talk now about the cerebrospinal fluid. Cerebral spinal fluid. Sorry for the slight hiccups in my writing at times. This pen has these random buttons on it. I don't know if you can see them. And I don't even know why they're there. Yeah, there you go, random buttons. I don't even know why they're there, but every time I press them, it messes up the text. I'm guessing it's there for people who are more experienced with this than I am. I'm not experienced with this. So these buttons, I'm just like, why are they here? I'd rather they didn't. Maybe I'll just tape them down. I don't know. That'll be something for me to contemplate on my own time. So what properties does cerebrospinal fluid give the brain? And the first is buoyancy. Let me make sure I'm spelling that right. Embarrassed to say this, but my undergrad was in English and I can't spell basic words. But again, that's a me problem. Buoyancy. So you probably know that if you put something in water, it's going to sit on top of the water, or it's going to be more, I guess you can say, I don't want to say weightless, but it's going to bounce. It's going to be contained within the fluid medium. And what that does is it is going to oppose force. It is going to oppose movement. It's going to create bounce. So buoyancy allows for reduction of movement based on fluid medium. So it creates the brain, it kind of makes it bouncy, and it reduces the intensity of its movement. In physics, you probably recall that it's called buoyant force, I believe. I think it opposes gravity or normal force, but it's been a while since I've taken physics and not an experience I really want to repeat. Next is cushioning, and it protects it from trauma. So liquid is not very compressible. And because of that, if the brain is bathed in it, then let's say that something happens and your head flies forward, or you hit or you bump into a wall. What's going to happen is that yes, your brain is going to shift, but the cerebrospinal fluid is going to sit between the brain and the cranium, and it is going to help to cushion the brain. It's going to prevent it from hitting against the brain. Normally, this is a very effective mechanism, but if you have a severe head trauma, which we see often in sports, then that's when the force is so severe that it actually displaces the CSF. And we'll talk about that toward the end of the lecture. Now, the next is it is a great transport medium. Because as we know, all nutrients plus gases must travel through water. And since it surrounds the brain, it can act as a transport medium. Now, talking about the composition. The composition is going to be, well, not much of anything, because as I said, the CSF is, well, I don't think I said this yet, but it is extremely selective as far as what can diffuse in and out of the structure called the choroid plexus. And mainly it is going to be very few to no proteins. Few to no proteins. Large things are not supposed to get into the CSF. Also, there should be no cells outside of microglia and neurons. So I'll just put down no foreign cells. Foreign means outside of its natural environment. If there are cells in the cerebrospinal fluid, then something has been compromised. We also have ions because ions are needed to maintain the proper electrical environment of the brain. And of course, we need lots of the sugar molecule glucose because that is what the brain prefers to operate on. So you should be seeing almost no proteins, no foreign cells, but a concentration of ions and a high concentration of glucose. All right, so that is our talk on the cerebrospinal fluid. Now we're going to talk about the blood-brain barrier. So the blood-brain barrier, as I talked about before, I'm going to draw it here, it is comprised of capillaries. And if you recall from anatomy, these capillaries are made up of cells called simple squamous epithelium, and on occasion basement membrane. And these are what we call continuous capillaries because we don't want space between these cells. So these are simple squamous cells. We know they're cells, so we have to draw a nucleus. But the problem is that capillaries, by their very nature, tend to be on the leakier side. So that's why we are going to surround them with astrocytes, cells with star-like processes. So we're going to draw some astrocytes here. They don't really look like this, but being an art major is not a requirement to teach this course, thankfully. So we have astrocytes here doing their thing. And astrocytes do a lot of jobs, as we talked about. This is only one. Reinforces the blood-brain barrier. And because of that, it creates an extremely selective environment. Now, what's interesting here is that these cells, they are going to prevent a type of transport called paracellular transport. Because of the composition of these capillaries and of the astrocytes, we are not going to have paracellular transport. And because of this, we eliminate a lot of things that we don't want getting into the intracellular environment of the brain. So what can be transported? Keep in mind that this is actually a very important part of developing some pharmaceuticals, is designing a medication in a way that can pass through the blood-brain barrier. Medicines made in the mid-1900s tended to be not very selective. And there was a type of medication called an antihistamine, and um, and back in the 50s, they designed one that goes by the brand name now, Benadryl. And Benadryl was able to pass through the blood-brain barrier. And as I was talking about before, is depending on the receptor, ligands can have different effects. So Benadryl is an antihistamine, which in the body helps to prevent allergic reactions from happening, or at least to mitigate their effects. But in the central nervous system, it causes feelings of sedation, which is why when you take a Benadryl, you get very tired. On the other hand, newer classes of antihistamine are not designed to pass through the blood-brain barrier. Because of that, they're more selective in targeting just the effects of an allergic reaction. But nowadays, if you are going to make a psychiatric medication, it has to be able to pass through the blood-brain barrier. All right, so ions. Ions are actually going to be transported. I'm going to draw them in yellow. Ions, they're actually going to be transported through carriers. So carriers are going to transport ions from the blood into the intracellular environment, and also vice versa. So ions can travel through carrier-mediated transport. Now, glucose travels through what is called a GLUT carrier. So glucose, they actually travel through what's called a GLUT carrier, which we talked about those before. But what's interesting is that these cells, they are insulin independent. Body cells, they will not transport glucose unless a molecule called insulin binds first. Insulin binds with the cell, gives it the okay to transport glucose. However, cells in the brain, they are insulin independent, and the GLUT transporters can move glucose without insulin. That's very important. That's why someone can be a diabetic, type 1 diabetic, for example, and not know, because their brain is functioning fine, but the effects are seen in their systematic body cells. Okay, next are amino acids. And these are very important because many neurotransmitters, as we talked about, are based on amino acids. So these need to be able to transport. This is also carrier mediated. So you're seeing that everything is very tightly controlled here so far. So amino acids, carrier mediated, very selective. Next is neurotransmitters. So to give you an example, let's talk about the neurotransmitter or the neuromodulator histamine. But when it gets in the brain, it acts like a neuromodulator. Let's say that we have one like what's found in Allegra. I'll put an A here for Allegra. It is a neuromodulator, apologies. But because of its composition, it cannot pass through the blood-brain barrier. Now, the same thing would happen if there was dopamine, for example. If you were just to take a medication that supplied dopamine, it actually would have effects on your cardiac system, but not your brain, because dopamine cannot pass through the blood-brain barrier. However, a precursor called L-DOPA can. So not all neurotransmitters or neuromodulators can pass through the blood-brain barrier. So neurotransporters / modulators they cannot pass through. All right. And next is going to be drugs. Drugs must be specially designed. They must be designed to be small and nonpolar. I've I've noticed, and I haven't done a lot of research on this, but drugs designed in the earlier 1900s, they were very general and non-selective. To give you an example, one of the medications that was talked about ad nauseum a couple months ago, hydroxychloroquine, was actually designed in the around the World War II era, and it's extremely general, has numerous effects in the body, which is why it can be used for everything from autoimmune diseases to malaria infections. So they do a lot of things. The downside is they also cause a lot of side effects. Generally, the more selective, then the fewer the side effects. All right, well, we talked about a couple things here. We talked about the fluid compartments of the central nervous system. We talked a bit about the cerebrospinal fluid and its composition. We talked now about the blood-brain barrier and what can pass through. And we also talked a bit about just some fun, interesting facts. All right, so next we're going to move on to basic sensory reflexes, and I'll see you there in a bit. All right, everybody, well, welcome back to the last part of our modified chapter 9. And now we're going to talk about something called a head injury, and hopefully none of you have had something like this too severe. But head injuries are broken up into two categories: primary and secondary. So primary head injury is when something severe happens, some sort of force to the head, or maybe you strike something with your head. And what happens is that the brain is actually going to move with such force that it's going to smash against the cranial cavity. So it's going to be a significant force. So primary is going to be the acute injury. However, secondary is going to be caused by the formation of what is called a space occupying lesion. And what's going to happen here is that you are going to have an increase in what we call intracranial pressure, which we'll define in just a moment, which can cause further injury. So when somebody incurs a primary head injury, the damage has already been done. But the race is on in order to ensure that someone does not develop the complications associated with secondary brain injuries. So before we go into this, we're going to talk about some concepts here. And this is kind of a preview of what we're going to talk about in later chapters. But we have a term called cerebral perfusion pressure, abbreviated CPP. And what this is more or less the net flow of blood through the arterioles in brain. We haven't talked too much about arterioles yet. They are smaller vessels that branch off from arteries, and under pressure, they are going to transport blood throughout the vessel. And the vessels in the brain, they also need to transport blood, make sure that blood is moving through a fairly good pace in order to make sure that all the neurons in the brain are getting enough oxygen and nutrients. Now, CPP is determined by two values. One is going to be called IP for intracranial pressure, and the other is going to be, actually, let me reverse this, MAP, mean arterial pressure, minus IP, which is intracranial pressure. So first, let's talk about MAP. What MAP is, stands for mean arterial pressure. And this is the force of blood movement through arterioles. Or arteries in general. When we talk about the brain, we're going to talk about arterioles. Mean arterial pressure is an estimation of the average pressure that blood is moving throughout your body. We call this mean arterial pressure. It's a more accurate reading, I believe, than just systole and diastole. And mean arterial pressure in the brain is probably about 100 millimeters of mercury. We'll define pressure later on, but pressure is force against the walls of a container. So only closed systems can be pressurized. And it's about, in the brain, about 100 millimeters of mercury. That is the mean arterial pressure throughout the arterioles in the brain. Now there's this other term called IP, or intracranial pressure. And the cranial vault is a closed system. And the brain is actually under a little bit of pressure. If one were to take the brain out of the cranium, they wouldn't be able to put it back in, because now the brain has expanded because it is no longer under intracranial pressure. So this is pressure that opposes MAP in the brain. I'll draw a quick diagram of that in a moment. And it's approximately 10 millimeters of mercury, give or take some. Millimeters of mercury is a unit we use in physiology to quantify pressure. So mean arterial pressure is the force of blood that moves through the arterioles. Intracranial pressure is pressure exerted on the brain because it is encased in a closed system, a closed vault. And to find cerebral perfusion pressure, the net flow, we need to subtract mean arterial pressure and intracranial pressure. So this here is going to be the cranial vault. It is a closed system. And right at the base is going to be this large hole called the foramen magnum. The cranium is made out of spongy bone, for those of you who need an anatomy refresher. And of course, in this thing here, we have the brain. So the vessels moving through the brain, this is a rather large vessel, but it'll give you the idea. Blood moves throughout the arteries and arterioles through the contractions of the ventricles of the heart. The heart's going to contract like this, and blood is going to be squeezed through the arterial system. So blood basically moves in spurts, and then, well, I'm getting into some complicated things that I'll talk about later. But when your heart contracts, blood is going to be stored in the walls of the arteries, then it's going to relax and it's going to be massaged through. Think of it like blowing up a balloon and seeing the walls of the balloon expand. Then if you take your mouth off the balloon nozzle, then the balloon's going to collapse. It's kind of what happens with our arterial system is we have contraction, slightly expands, then when the heart is in diastole, it's going to relax and the blood is going to move through. Systole, the heart contracts and the walls of the arteries are going to be pressurized. Diastole is going to relax, that pressure is going to be relieved and blood is going to move through. So that's just a brief introduction, but we average the flow that happens during systole and diastole, we call that MAP. So mean arterial pressure is going to push against the walls of the arteries or arterioles, and it's going to move against them. It is going to push against the walls to move forward. So mean arterial pressure is essential. Pressurizing these walls is essential for blood to travel through the arterial system at the appropriate speed. So this is MAP. Now what opposes MAP is going to be intracranial pressure. It is going to oppose mean arterial pressure. Think of mean arterial pressure as trying to push out. Intracranial pressure is trying to push in. Now, thankfully, though, mean arterial pressure is a lot more forceful than intracranial pressure. Because of that, cerebral perfusion pressure is going to be, so CPP equals MAP minus IP. So it's going to be more or less 90 equals 100 minus 10. So on average, cerebral perfusion pressure is going to be 90. Great. Now what's going to happen when somebody gets a head injury? Well, what is going to happen is that the brain is going to slap against the cranial walls and it's going to become damaged. The brain is tissue like anything else. If you hit it forceful enough, it's going to be damaged. What's going to happen is that you are going to have an acute injury. And then what's going to happen, if any of you have ever had a concussion, hopefully not, is at first you're going to get a hit, you're going to get your bell rung a bit, as they say. Then you're going to be like, oh, okay, well, I'll be good. I can get back to the game. Well, when you first have that injury, we call that an acute injury. The problem is that tissue that is well perfused with blood, when it is damaged, it starts to bleed. You have broken vessels. So what's going to happen is that we are going to have something occur called hemorrhaging. So what's going to happen now is that we are going to have, let me make sure I spell this right, hemorrhage. But what's going to happen is that you are going to have the non-technical term called bleeding in the brain. Now you're seeing what's developing now is a mass. We call this mass here, and this is a very important term, we call this mass a space occupying lesion. And this is really bad for us because what's going to happen is that we already have pressure, intracranial pressure, because the brain is enclosed in an enclosed system. Because of that, it's going to slightly pressurize the brain. Well, recall also that pressure is defined as force against the walls of a container. If you force more things in the walls of, or if you force more things in the same size container, then you are going to increase pressure. And the problem is that as this space occupying lesion grows because of increased hemorrhaging, you are going to have increased intracranial pressure. So the larger the hemorrhage, the greater the increase of intracranial pressure. And this isn't good because as this number goes up, this number goes down. And this is when we start to get the symptoms of a secondary brain injury. Because now we have this space occupying lesion that is taking up space in the cranial cavity. Think of it as being in an elevator. And at first you have a decent amount of space, door opens up, 5 people cram their way on, you're stuck in the corner like this. Now you have people pushing against you, and the elevator has not gotten any larger. So in this case here, the space hasn't gotten any more volume, but now it has this blood mass taking up space. All right, so the effect is that it is going to increase intracranial pressure and decrease cerebral perfusion pressure. Now, why is decreasing cerebral perfusion pressure bad? So CPP is about 90 normally. As CPP decreases, perfusion of blood in brain decreases. So to break it down a bit, less blood flow results in less oxygen available to cells, less nutrients available, and the brain is one of the organs that really does not like to be deprived of oxygen or nutrients, and its function is going to be inhibited. So it's going to result in impaired cognitive function. So what this means is that if somebody has an acute head injury, and then they start to develop a space occupying lesion, what's going to happen is that cerebral perfusion pressure is going to go down. The brain is going to get less oxygen and less nutrients, and the patient is going to begin to develop symptoms of a secondary head injury. Now, one way that we measure that, we measure the effects of this secondary injury, is called the Glasgow Coma Scale. And you can look it up online if you work as in a nurse or EMT, or you know someone that's an EMT, a nurse or doctor. I'm sure they can tell you more about it. You can go online. But this will measure how much brain function has been affected by a secondary head injury. This increase in intracranial pressure, what's also concerning about it is that if it gets too severe, is recall that we have this hole here called the foramen magnum. What I like about Latin, they're very blunt. Foramen means window, magnum means big, so it literally means big hole. Sorry, foramen means hole, magnum means big, so it means big hole, and that's exactly what it is. It's a big hole. And what happens is that this big hole, the brainstem fits through, but if intracranial pressure gets too intense, recall that intracranial pressure presses down on the brain, is that it can actually force it down into the foramen magnum, basically causing permanent brain injury and possibly death if the brain is actually forced through this hole. So secondary brain injuries are to be taken very seriously. And that's also the reason why if somebody gets a concussion, why ideally do not want them to go to sleep because they could be developing symptoms of a secondary head injury without you knowing it. So you need to, it's important to keep them awake so you can assess whether or not they're having any impairment in cognitive function. All right, so we talked a bit about head injuries, just the basics of it, and some of these factors too, like mean arterial pressure and things like that, we'll be covering a lot more in the later chapters, and by later I mean probably next week. But hopefully this gave you a brief background information on a topic that's a pretty serious topic, because we know that in sports, especially as athletes get stronger and more powerful, well, then you are seeing an increased prevalence of concussions, and we've only really begun to respect the effects of concussions probably in the last 15, 20 years. So it is important to learn about why exactly secondary brain injuries are so why it's so important to keep track of them and seek treatment if necessary. All right, over and out. Next time will be chapter 11. All right, everyone. Hello, welcome back. So we are now on chapter 13, and I'm going to actually take the L and go with the PowerPoint on this because it's a lot of text and it is also a lot of pictures that I can't really draw. So here we are. Let's go with the PowerPoint. It's chapter 13 PowerPoint. Feel free to pause on any version that you want to focus on, and then we'll go from there. All right, so anyways, going to our PowerPoint here. So we're going to talk about the different classes of receptors. And basically, there are two types of receptors, or actually three classifications: exteroreceptors, interoreceptors, and proprioceptors. The exteroreceptors, what they do is that they're going to detect stimuli that comes from the outside of the body. And mainly it's in the integument system. We call these special sense organs, well, actually, it isn't fair to say mainly in the integument system. It's anything where the stimuli comes from outside the body. So, for example, visual, auditory, mechanical, taste, smell. So anyways, these are things that detect stimuli, so that's their job. They detect stimuli that happens to you, from the outside environment to you. And really, that's what sensory neurons do, is they help us to navigate the world around us by feeding information to our brain. Now, the next one is called an interoreceptor. And these are things that largely you don't even realize. For example, right now, there are special receptors in your blood vessels that are determining how much they're being stretched by your by the flow of blood. And if they're stretched too much, they're going to do changes in order to reduce blood pressure. If they aren't stretched enough, they're going to make changes to increase blood pressure. Now, most people are not even close to aware of their workings. For example, the endocrine system is going to use chemical messages called hormones to alter cellular activity. And this all is going to happen without you knowing it. So in internal receptors, what these do is that they monitor the current state of your body. They keep track of the current state of your body. And they make the necessary adjustments in order to ensure that your body maintains its preferred set points. Now, the last ones are proprioceptors. Now, I don't like to stretch. It gets painful, it's uncomfortable, and it's boring. So what this does is it helps you to determine the current state of your muscles, ligaments, and tendons. And you can activate them simply. You can just go like this, stretch your shoulder, you'll feel a nice stretch. That is detected by your proprioceptors. You also probably know that it's going to be a really bad idea to take your elbow and try and bend it, try and hyperextend it. That's because there are these receptors in your joints and ligaments that tell you when they're being overly stretched. So basically, the idea is to prevent injury, really. And by giving you the feeling of stretch, it's going to let you know whether or not what you are doing to the muscular system and supportive system, and letting you know whether or not what you're doing is good. So it helps to maintain a proper range of motion, and it helps you understand when the muscle is being stressed too much. Of course, the idea behind stretching is that you're trying to improve the flexibility of your connective tissue to the point where it is no longer stressing the body. So it's actually rather good to be a little bit flexible, because you can do things like increase your range of motion, and also ensure that you don't have those tight muscles that can help to impede blood flow. Really, also they're intended also to communicate with your brain and let you know the current state of your muscle system, whether or not you are walking, whether or not you are lifting. So it pretty much helps to tell your brain which muscles are working. So it's also responsible for communicating which muscles are moving and in what direction. But it's also intended to prevent injury and overstretch. Okay, so now we're going to have classes of sensory receptors. The first one is called a mechanoreceptor. And this detects any kind of mechanical stimuli. And as I said, including auditory, because sound is actually in waves. Many of you know that if you go to a concert, well, if you did pre-COVID, you will know that it's actually, you can actually feel the vibrations of the bass, for example. So that's just further evidence that sound comes in waves. So anything that is physical touch, anything that is happening to you physically, activates a mechanoreceptor. Thermoreceptors, what they do is that they're actually going to detect changes in temperature. And believe it or not, there's actually two types of thermoreceptors. One is going to detect heat, and the other is going to detect cold. So you actually have two sets of thermoreceptors that each detect either heat or cold. Photoreceptors, these respond to light energy, and not going to be honest, or sorry, not going to mince words. Anything outside the eyes is probably not going to have a photoreceptor. So these are found in your eyes, especially the retina. Next is chemoreceptors. This is mainly anything that is going to respond to chemicals. Now, cells can receive chemicals from other cells and change behavior. But also things like smell and taste, these are other examples of chemoreceptors. Now, many people say, well, when you wear a mask, you can still smell things. So how is it protecting you from a COVID or viruses? The answer is the particles that our nose picks up to activate smell, they're actually several magnitudes smaller than viruses. So these particles are much smaller than the viruses even. So it really is not a fair comparison. It's saying like, why can a cat door why can a cat door actually, where am I going with this? I have no idea where I'm going with this. Anyways, yeah. Anyways, viruses can't get through the mask, especially if they travel in water droplets. But particles that cause smell can't, because they're much smaller. Okay, yeah, it's kind of like saying a cat can't get through a mouse hole, but a mouse can get through a mouse hole. Does that even make sense? Maybe, but I'm not gonna to press the issue anymore. Good analogy, bad analogy. I'm taking the L. Nociceptors, what these do is that they detect pain, and they never you never get used to the brain or the pain. As we'll talk about, is that there's certain kind of sensory receptors that we call phasic and tonic, meaning that I believe it's phasic. Let me just double check here. Phasic, I believe the stimulus can actually change, or sorry, the response to the stimulus can change where you get used to it. Tonic, on the other hand, there's no getting used to it. Nociceptors are tonic, meaning that there's no getting used to them. You don't get used to pain. Pain is an unpleasant sensation. It doesn't matter if it happens to you once every 10 years or once every 10 minutes. It's going to continue to be the same unpleasantness. And that's good because you don't want to get used to pain, because that means that your body is going to get hurt. Okay, now moving on, we're going to talk about major features of sensory reception. Let's find it here. Major features. Okay, cool. Okay, give me 1 second. Okay, yeah, so first we are going to talk about, and this is a little bit lower, phasic and tonic. Let me see where that is. Yes, so it is the next one. So we're going to talk about receptor level, specificity. All right, well, I'm not going to try and find it on the PowerPoint. I'll just go ahead and explain it. So basically, what receptors do is that they are going to generate a signal. But keep in mind, the body reacts to something or specializes in something called specificity. And we see that, for example, in cells, where there's several parts of the cell that each has its own responsibility. Well, sensory neurons are the same thing. Stimuli, auditory stimuli, so on and so forth. There's each neuron is going to detect a different stimuli. Called specificity. So each type of neuron is going to detect a different stimuli, and it's going to be very good at it. Now, next is going to be sensitivity. Certain receptors are much more sensitive than others. For example, Merkel cells, the cells we talked about that are in the epidermis, they're extremely sensitive, as in you can activate them even with a little bit of touch. Others, though, for example, nociceptors, you need a pretty significant stimuli to activate the nociceptors. Now, some of them are extremely general, meaning that you can feel them over a wide range. Others are super specific, meaning that you have to be felt in a very small range. For example, Merkel cells are in a very small field, but then again, for example, receptors that detect pressure are a rather large field. And next is going to be transduction speed. We talked about that idea of myelination. And basically what this means is that the more heavily myelinated a sensory neuron is, the faster information travels to the brain. Now, if it is heavily myelinated, it's going to go to the brain really fast. However, if it is not myelinated, it's going to travel slower. However, there's certain neurons that are very close to the brain, like for example, the optic nerve, doesn't need to be myelinated because it's already very close to the brain. So basically, the more the myelination, the faster the signal is going to be transduced to the brain. So we're going to talk about two types of adaptations. Well, more like whether or not it's going to adapt or not. Now, let's say there's a constant stimulus. Your body has two options here. One is for you to adjust to the stimulus, meaning that the neuron is going to activate, it's going to be very powerful, and then all of a sudden it's going to get weaker. So what's going to happen is that at the beginning, you are going to see lots and lots and lots of action potentials. But then, if the stimulus is kept the same, it is going to it is going to fire less and less of action potentials. Probably easier at this point if I just draw it on the board. Okay, cool. So this is a phasic example. So this is a phasic. What a phasic neuron is that it is going to trigger action potentials frequently at the beginning of stimulus or if stimulus changes. Or if the stimulus changes. Okay, so basically, if we are going to have a graph here, we're going to have here stimulus applied, and then stimulus increased, going to look like this. But then it's going to become less frequent and less frequent until it stops. And you get used to it. Then if you increase the stimulus, it's going to go like this again and then stop. To give you an example of this, take your finger, press down on the desk lightly. You'll feel pressure. Those receptors are firing in order to deliver the sensation of pressure. But if you keep on pressing down the same, the action potentials will stop and the neuron will be deactivated temporarily because it is phasic. You've gotten used to it. But if you press down even harder, those action potentials are going to resume, then turn off. So that's phasic. Now tonic, on the other hand, tonic, there is no adjustment with constant stimuli. So basically we have something here. So we have, what we are going to do is we're going to have application of stimuli. It's going to go like this. Now notice how the body's never going to get used to it. Sorry, body. Notice how the sensory neuron is never going to get used to it, to the stimuli, and reduce the amount of impulses. The impulses are going to stay the same. So it is going to be constant impulses. Great example of this is going to be thermoreceptors, and those receptors, you just don't get used to being cold. You just don't get used to being hot. You're going to continue to feel hot and cold. And the same thing with pain is you're not going to get used to feeling pain. It is going to either, you're either going to feel it or not. There's no adjustment period. Let's go back to the PowerPoint that I was talking so highly about. Okay, so now we're going to have different types of perceptions, or sorry, major features of sensory reception. And the first is perceptual detection. So this is our ability to detect a stimulus, meaning that this is the ability for the neuron to actually do its job. Next is what we call magnitude estimation. So what this is that neurons have the ability to detect how intense the stimulus is, and they'll adjust their signal to the brain depending on that. Now next is going to be spatial discrimination, where basically you are going to detect where the stimulus is applied and in what pattern. Now, of course, in lab we do something called a 2-point discrimination test. One thing you can do though, if you want to do it with a friend, is you can have them, hey, point or poke me somewhere. Okay, they poke you, then you say, okay, well, I thought you think you poked me here. So what they do is that they take a felt tip pen, they poke you, and then basically you touch where you think the stimulus was, and then they measure how far that distance was. So spatial discrimination means that you are going to know where the stimulus was applied and in what pattern. Next is called feature abstraction. This one is kind of interesting. So there's certain neurons, there's certain receptors that can detect many different complex things. So for example, like it can determine, okay, well, what kind of stimulus is this, and what is the pattern of it? And I know that doesn't make a whole lot of sense, but it is a bunch of different aspects of neuronal communication, all sort of detected by the same neuron. I guess an example of this would be, okay, so you touch ice, it feels cold. You touch really cold ice, like let's say it's really frozen, and it feels like a sharp cold. So basically, it's like detecting different types of cold. I don't know if that makes sense, but basically just know this definition, knowing that it's ability to detect several complexities of stimuli. So that means another example, you can detect the heat from a dry desert wind compared to the heat from a stove. Now next is quality discrimination. So for example, we know about taste, is that neurons that make up the taste receptors, they can detect either, for example, sweet, sour, bitter. So what it does is it helps you determine different qualities of the stimuli. Great example of that is going to be taste and smell. So it isn't just smell, it's, I don't know how to describe smell. It smells sweet, smells sour, smells toxic, so on and so forth. So it's like different variations of the stimuli. Next is going to be pattern recognition. This is becoming familiar with something. So for example, you see a dog, you realize that a dog is not very harmful. You hear a tune and you are able to hum back the tune. Somebody plays your favorite song and you're able to detect it as your favorite song. So basically, it's the ability to detect a sense, is the ability to detect a certain pattern and recognize it. All right, so that is the end of chapter 13. Hope you all enjoyed chapter 12 and 13 lecture.